Good afternoon, everybody, and welcome to part 2 of Mastering Buffer Calculations with Miss G. In part 1, which was uploaded to YouTube last Tuesday, I talked through how we can prepare acidic buffers, what buffers actually are, the two methods of preparing them, and then how we can calculate the pH of the buffer solution. So if that's something that you feel you need to watch first, that video is already live on my YouTube channel. In the second part of this mini-series, we're going to have a look at how buffers are able to maintain their pH when small amounts of acid, alkali, or water are added to them. So questions may potentially ask you as a part 1 to calculate the pH of the buffer solution initially, which is covered in the part 1 video. And then in the second part of the question, they may then say that you're going to be adding an acid or an alkali to that buffer, and you would then have to prove that the pH of the buffer will be maintained and won't change. Now, it may change ever so slightly, i.e. within plus or minus 0.01 or 0.02 pH units, but the ratio of the weak acid and the salt stays almost constant, which means that the hydrogen ion concentration also stays almost constant, and thus we can say that the pH of the solution is maintained. So today what we need to understand is when we are adding an acid to a buffer, what does that do? How does that shift the position of equilibrium for the weak acid dissociation equation? What does that therefore mean for the moles of the weak acid and the moles of the salt? And once we've worked that out, we can then input those new mole values into the same rearranged Ka expression we were using in part 1, and from there we can then get the pH. And it's the same thing when we add an alkali. We need to think about how adding the alkali shifts the position of equilibrium, and then what that does to the moles of the weak acid and the moles of the salt, and then again we can just sub those new values for the moles into the rearranged Ka expression to get the hydrogen ion concentration and thus the pH. Now, when the position of equilibrium shifts, the reason why the buffer maintains its pH, like I said, is because the ratio of the weak acid and the salt stays almost constant. So what we should be seeing in part 1 and part 2 of the two examples I'm going to go through with you now is that the pH is either identical or, like I say, out by perhaps 0.01 or 0.02 pH units. So let's talk through addition of an acid first. You can see that I've written out the steps of the method for what you need to be doing when you are presented with a question that says that you are going to be adding an acid to a buffer. I've done the same thing for the addition of an alkali to a buffer, and you will notice that the wording is identical, with the exception of obviously what change occurs, so which way the position of equilibrium shifts and how the moles are changed. But in terms of the order of the steps, they are identical. And then what we will do is we will have a look at two examples, both of which are a part 1, which is calculating the pH of the buffer initially using the skills from the part 1 video, and then part 2, which is what we're focusing on mainly in this video, which is what then happens to the pH of the buffer after the addition of either the acid or the alkali. So let's get stuck in. So when we add an acid to a buffer, we need to know how many moles of acid we are adding. Sometimes they will give you the moles of the acid, sometimes they'll give you a volume and a concentration, and from there you can work out the moles. Now, using our knowledge of the position of equilibrium and how that can be shifted from year 12, we need to understand how adding an acid will shift the position of equilibrium for the weak acid dissociation equation that I've highlighted there in the yellow. So the weak acid dissociating slightly into H plus and A minus. Now, if I add an acid, I am adding a source of H plus ions. So if I add more H plus ions, the position of equilibrium is going to shift left to use up or remove the added H plus ions. And if the position of equilibrium is shifting to the left, then that means we are going to make more of the weak acid, HA, And we're going to lose some of the salt, the A minus, because that's going to react with the added H plus ions to get rid of them, leading to the formation of more of the weak acid. So the amount in moles of the weak acid will increase by the number of moles of acid that we have added to the buffer. And the amount in moles of the A minus, which is the salt, will decrease by the number of moles of acid added, because the salt is going to react with the added H plus ions and they react in a 1-to-1. So whatever moles of acid we're adding, we're going to lose that same amount of A minus, and that will then make, because they're all in a 1-to-1 ratio in this equation, that many moles of weak acid. So we take the initial moles of the weak acid and we add to that the number of moles of acid added, and then we take the initial moles of salt that we had and we decrease that by the number of moles of acid added, and then those two new values for the moles of the weak acid and the salt go into the rearranged Ka expression with our value for Ka. Then we can get the H plus concentration, and then we can get the pH. Now we're thinking about the exact same things when we are adding an alkali, but when we add an alkali, the position of equilibrium is going to shift the other way. So the first step is the same. We first of all need to calculate the moles of alkali that we are adding, which again, it may be given as moles already, or it may be that it's given as concentration and volume. The position of equilibrium this time is going to shift to the right, because in adding an alkali, we are adding OH minus ions, and those OH minus ions that we add react with the H plus ions in our weak acid dissociation expression. If we are thus removing H plus ions from the equilibrium, we're reducing their concentration. The position of equilibrium will shift to replace those H plus ions that are lost. And when those H plus ions are lost, because they're reacting with the OH minus ions from the alkali, water is formed. That shifts the position of equilibrium to the right, meaning this time we're going to lose some of our weak acid, but we are going to gain more of the salt. Again, how much weak acid we lose is the same as the moles of alkali added, and how much of the salt we make, or we gain, is the same as the number of moles of alkali added. Once we have those two new mole values, again, we're putting them into the rearranged Ka expression to find our H plus concentration and thus find our pH. So when I work through these two examples, as I've already said, step 1 in both cases is working out the initial pH of the buffer using the skills from the last video. When it comes to part 2, this is when I will be following these steps here. Now, I'll show you how I would lay it out. Of course, I'm not saying that you have to lay it out in exactly the same way, but however you choose to do it, please make sure that you're setting things out logically, both for yourself, so you know what the numbers mean that you're writing on the piece of paper, but also for the examiner as well. Because if you got a question like this in an exam, they could be worth up to 6 marks. And if you don't happen to get the right pH value at the end, they will look to try and award you method marks for all of the steps that you have done previously. But that's only possible if how you've laid out your working out is legible and logical and easy to understand for the examiner. So my advice would always be to be really clear on what it is you are doing. So I'm not saying my way is the only way, but my way will be clear to an examiner marking my answer. Heaven forbid I get the answer wrong. So let's dive in and have a look at these two examples. Okay, so let's have a look at this first example here. So it tells us that a buffer is prepared by adding 0.0122 moles of our salt, NaY, to 40 centimetres cubed of a 0.210 mole per decimetre cubed solution of the weak acid, HY. We've then been given the value for Ka for the weak acid, which is 1.71 times 10 to the minus 5 moles per decimetre cubed. And in part 1, we're being asked to calculate the pH of the buffer solution formed. So we've already been given the moles of the salt as 0.0122, so there's no calculations required for that. But for the weak acid, we have been given a concentration and a volume. So the first thing we're going to need to do is work out the moles of the weak acid that we have, making sure that we convert our volume to decimeters cubed. Which is 0.0084 moles. And then we've been given our value for Ka. So we can write our Ka expression as the concentration of the H plus ions, the concentration of the Y minus ions divided by the concentration of HY. And in part 1 of this little series, I talked about how we don't need to use concentrations for the weak acid, HY, and the salt Y minus, and that instead we can use the moles and that this was far easier. So when I now rearrange my Ka expression to get H plus equals, I'm going to drop the square brackets for HY because I'm going to use the moles of the weak acid, and I'm going to drop the square brackets for the moles of the salt, the Y minus, because again, I'm going to be using moles, not concentration. And now we just need to sub those numbers in. So the H plus concentration is going to be equal to the value for Ka, which was given to us in the question as 1.71 times 10 to the minus 5. I'm then going to times that by the moles of the weak acid, which is 0.0084. And then I'm going to divide that by the moles of the Y minus, the salt, which was 0.0122. And I'll just do that on my calculator now. Which gives me 1.18 times 10 to the minus 5 moles per decimeter cubed to 3 significant figures. And then to calculate pH, pH is equal to minus log base 10 of the hydrogen ion concentration that we've just worked out. So to 2 decimal places, the pH of this buffer solution is 4.93. And that is exactly the same as method 1 that we looked at in video 1, where we're adding the salt and the weak acid together into the same container, vessel, beaker, conical flask, whatever it might be. Method 2, if you remember, was adding an alkali to the weak acid, with the weak acid being in excess to make the salt in situ, which isn't what I've had to do here. So now we're going to come on to the focus of this video, which is what now happens to this buffer when I add, as it says in part 2 of the question, 2 times 10 to the minus 4 moles of hydrochloric acid. We now have to calculate the pH of the buffer solution after that acid has been added. So I'm just going to very quickly scroll back up to what I need to be doing. So I need to work out the moles of acid that have been added. They've given us the moles already in the question, so that's great. Then we need to think about how the position of equilibrium is going to shift and how that's going to affect the moles of the weak acid and the moles of the salt that we've just used in part 1. Then we're going to sub those new values in. Okay, so let's have a go at that. So first up, I'm just going to write down the moles of hydrochloric acid added, so that I have that information easily to hand. 2 times 10 to the minus 4. Then I'm going to write my dissociation equation. I'm not going to use HA because they gave us it as HY. So HY will slightly dissociate into H plus and Y minus. Now, I am adding more H plus. So I'm going to do a little red arrow underneath there to show that that is increasing. If the amount of H plus is increasing, that is going to shift the position of equilibrium to the left because the system is going to want to use up the extra H plus that I am adding. And that means that the amount of Y minus the salt is going to decrease because the Y minus will react with the extra H plus ions, and that means we're going to make more of the weak acid HY. So I'm going to show that using those little green arrows, as visually for me, I find that very helpful. So now I know how many moles of HCl have been added. I know that that's how much of the H plus is going to react with the Y minus. So that's how much of the salt we are going to lose. So I can do my original moles of salt from the first part of the question, which was 0.0122, and I can take away the amount that I'm going to lose as the Y minus reacts with the extra H plus, which gives me 0.012 moles of the Y minus after some of it has reacted with the extra H plus. And now I need to do the same thing with the HY in terms of changing the number of moles, but this time we're going to make more of the HY, because as the H plus ions get used up in reacting with the Y minus, we're going to make more HY as the position of equilibrium is shifting to the left. So the original moles of the weak acid was 0.0084, and this time I'm going to add to that the moles of the HCl that was added. Which gives me 0.0086 moles of HY. And now that I have these new values for the moles, I can sub them back into our rearranged Ka expression. So I'm not going to write out the Ka expression and rearrange it again because it is written just above. I'm going to go straight to the concentration of H plus equals the value for Ka, which hasn't changed, so 1.71 times 10 to the minus 5. And then we're going to multiply that by the new moles of the weak acid, so apologies, 0.0086. And then I'm going to divide that by the new moles of the salt, which is 0.012. And that's going to give me a value of 1.23 times 10 to the minus 5 moles per decimeter cubed. And then from there, again, pH is equal to minus log base 10 of the hydrogen ion concentration. And if I put that in on my calculator, I get a value for the pH to 2 decimal places of 4.91. Now, as I explained at the start of the video, when we say that the buffer is able to maintain its pH, it doesn't necessarily stay identical. I did say it may differ by 0.01 or 0.02 pH units, as is the case here. And you can see that the hydrogen ion concentration does change ever so slightly, but essentially the ratio of the weak acid to the salt stays nigh on the same, and thus the concentration of H plus stays nigh on the same, and thus the pH is maintained. That's the official phrasing that we would use. I know it has changed ever so slightly, but we would say that the pH has been maintained. Now, this only works when we add quite a small amount of acid or alkali, so we're only adding 2 times 10 to the minus 4 moles of acid to our buffer. If we were to add too much acid or too much alkali, that ratio of weak acid and salt would not be maintained, and thus the pH would change. So it's really important that we understand that the pH can only be maintained upon addition of quite small quantities of acid or alkali, but that would be how you would do that question. And visually, I like how that's laid out because I can think about how the position of equilibrium is going to shift, what that's going to do for the amount of weak acid and salt. Then I can get my new moles, and then we're just subbing it into the same Ka expression that we used in part 1. And that would be it. All of that would be worth 6 marks. Potentially, maybe 5 or 6. As you'll see when you do practice questions, that's kind of the range of marks that we're looking at. And actually, my plan for next week's YouTube video, as sort of a part 3, is to do a worked example of a buffer question from a past paper. And that particular question that I'm going to choose to do is worth 6 marks. So look out for that as a sort of part 3 worked exam answer calculation next week. So let's have a look at the second example, which is dealing with addition of an alkali to our original buffer solution. So again, part 1 is going to be calculating just the pH of the buffer initially, and then in part 2 we're going to be adding sodium hydroxide this time to the buffer. So the value of Ka for methanoic acid is 1.78 times 10 to the minus 4 moles per decimeter cubed at 25 degrees. A buffer solution contains 0.0150 moles of methanoic acid, which is our weak acid, and 0.0120 moles of sodium methanoate, which is our salt, in 500 centimetres cubed of solution at 25 degrees. So step 1, calculate the pH of this buffer at 25 degrees, and then step 2, a 5 centimetre cubed sample of 0.120 mole per decimeter cubed sodium hydroxide solution is then added to that buffer. And we'll come back to that in a second, because the first thing we need to do is get the pH of the buffer initially. Now they've already given us the moles of both the salt, the sodium methanoate, which is 0.0120, and they've already given us the moles of the methanoic acid, which is our weak acid, and that is 0.0150. Now this is where using the moles is easier than using concentrations, because we can just use those numbers straight away. We don't need to worry about the fact that they're in 500 centimetres cubed of solution, because the volumes would actually cancel out of our Ka expression, so we can just use the moles. So Ka is going to be equal to the concentration of H plus times by the concentration of A minus divided by the concentration of HA. But of course, when I rearrange this, because I'm using the moles of the weak acid and the salt, I'm going to drop the square brackets. So Ka multiplied by the moles of HA divided by the moles of A minus. And then we can sub all of those values in. So the Ka value that we were given in the question is 1.78 times 10 to the minus 4. And we're then going to multiply that by the moles of HA, which is 0.0150. And then we're going to divide that by the moles of the salt, which is 0.0120. And I'll just work out what that is on my calculator now. 2.23 times 10 to the minus 5 moles per decimeter cubed. And then pH is equal to minus log base 10 of the hydrogen ion concentration. So for 2 decimal places, the pH of my buffer is 3.65. Okay. Now we can think about part 2. So how much alkali am I adding to my buffer? So the steps are the same as what we did for adding an acid to a buffer, but how the moles will change for the weak acid and the salt differs, but the steps that we're going to consider are identical. So how much alkali are we adding is the first thing we need to work out. This time we haven't been given the moles, we've been given the volume and the concentration, however, of the sodium hydroxide, so we can very easily work out the moles of that we have. So that's the first thing I'm going to do. So moles of NaOH, sodium hydroxide added, equals concentration times volume 0.120 times 0.005 decimeters cubed. So a very small volume, which is going to give us quite a small value for the moles, which, as I said earlier, a buffer can only maintain its pH upon addition of very small quantities of acid or alkali. So we've got 6 times 10 to the minus 4 moles. So not very much at all. Now, like I did last time, I'm now going to write out the dissociation equation for my weak acid. So HA dissociating into H plus and A minus. Now, when we add an alkali, the alkali takes away the H plus ions. So even though the alkali is not in this equation, the alkali will react with the H plus to give us water. And that is therefore going to reduce the concentration of the H plus ions. And subsequently, the position of equilibrium is going to shift to the right to replace the H plus ions that are taken out of the equilibrium in the reaction with the OH minus to make water. If the position of equilibrium is shifting to the right to make more H plus to replace what's been taken, that's also going to make more of the A minus, because you can't shift the position of equilibrium to the right and only make H plus, because for every one HA that dissociates, you make one H plus and one A minus. So that's going to increase the amount of salt that we have. But it's also going to decrease the amount of the weak acid that we have, because that is going to dissociate more to replace those H plus ions. So as we did last time, we can now amend the mole values that we had in part 1 and change them accordingly. So starting with the salt again, the initial moles of the salt was 0.0120, and this time we're going to gain moles of salt, and the gain that we're going to experience is by the amount of moles of alkali that have been added. So the 6 times 10 to the minus 4. We're going to add that to how much salt we had initially, and that'll give us the new moles of salt, which is 0.0126. And then for the weak acid, again, we need to know how many moles we had initially, which was 0.0150. But this time we're losing some of our weak acid, and the amount we lose, again, is equivalent to the amount of alkali that we add, because that amount of alkali will react with that amount of H plus to make the water, and that means that's how much of the H plus we need to replace. It gets replaced by that amount of HA dissociating, and that then generates the same amount of A minus. So if I work out what 0.0150 take away 6 times 10 to the minus 4 is, that will give me the new moles of the weak acid, which is 0.0144. And then with those new values for the moles and the original value of Ka that we were given of 1.78 times 10 to the minus 4, I can sub those three values into my rearranged Ka expression. And again, I won't write out the original Ka expression again because it is just written above. I'm going to go straight to the concentration of H plus being equal to the value for Ka, 1.78 times 10 to the minus 4, multiplied by the new moles of HA, which is 0.0144, and then dividing that through by the new value for the moles of the salt, which is 0.0126. That will then give me the hydrogen ion concentration. Which is 0.00203 moles per decimeter cubed, which of course we could write in standard form. I'm not sure why my calculator hasn't automatically given me that in standard form, but there we are. And that will then give us a new pH, which should be nigh-on identical to the pH that we had before. 3.69. So a slightly bigger change this time than we saw with the last example, where it only changed by 2 pH units. Here it's changed by a little bit more than that. But still, we can say that the buffer has maintained its pH. So that would be how you would answer these particular questions on buffers. And I really hope that seeing me attempt those 2 examples has helped you to see how to lay out the calculations. And obviously you've got the steps that you need to take for the addition of acid and alkali written there to help you. I really hope that part 2 of this video has been as helpful as part 1. I really hope you found both of them really useful for understanding how to approach buffer questions. If you have any queries about the video or you are attempting questions and would like some support, please feel free to reach out across any of my social media platforms or via email, and I will always be more than happy to assist. Thank you so much for watching. Don't forget, part 3 next week will be a worked exam answer of a buffer question. So again, you can see how I would take this approach and put it into another question. So hope to see you watching this video, and I hope to see you again watching next week's video. Thank you so much. Take care, everyone.